In this video, we'll explore key concepts in JAX, particularly focusing on arrays and transformations, which are fundamental to how JAX operates. JAX is a powerful system that abstracts away the underlying infrastructure, allowing us to use many different types of computing hardware. For our demonstration today, we'll use a TPU v5, which is a special type of processor available through Google. Whether you're using a free or paid runtime in Google Colab Pro, you can follow along with this tutorial. Let's begin with array creation. The first step is installing JAX itself. We need to do a pip installation at the beginning, and specifically, we'll choose the TPU variant of JAX for our installation. After installation, we can start working with arrays by importing both JAX and the JAX NumPy library. The JAX NumPy library provides an interface that is very similar to standard Python NumPy, which you might already be familiar with if you work with regular NumPy on CPUs. Just like in regular NumPy, we can use functions such as arrange to create arrays. When we create and display an array, you'll notice some important information about its type. JAX automatically determines, or infers, the type of data in the array, but we can also manually adjust these types if we need more control over our data. The resulting array is specifically a JAX NumPy array type. An important aspect of JAX arrays is understanding where they're stored in terms of computing devices. When we examine the devices portion of our arrays, we can see that by default, our array is stored on the TPU v5 chip. It's worth noting that JAX arrays can be distributed or sharded across multiple devices. We can check this distribution using the X sharding command. In our current setup, we're only using a single device, but in larger systems, these arrays could be spread across multiple devices or even multiple host computers. Let's explore some important transformations in JAX. There are three particularly significant transformations you should know about: JIT for just-in-time compilation, VMAP for automatic vectorization, and GRAD for gradient transformation and automatic differentiation. To demonstrate how these work, we'll create a practical example using a CLU function. The CLU is a mathematical function that we can optimize at runtime using the just-in-time compiler. When we implement this function, we can see that using the CLU function with an input value of 1 gives us an output of 1.05. There are two ways to apply just-in-time compilation to our function. The first method is to directly use the just-in-time compiler function. The second method, which many developers prefer, is to use a function decorator by adding @JAXJIT above our function definition. Both approaches achieve the same result. They create a just-in-time compiled version of our function. Next, let's understand tracing, which is the underlying mechanism that makes JAX and its just-in-time compiler work so effectively. Tracing is a process where JAX represents array operations in an abstract way. This abstraction allows JAX to extract sequences of operations and apply powerful optimizations to our functions. When we demonstrate tracing with the simple function that adds 1 to its input, we can see that JAX captures important information like the shape, a vector of length 5, and the data type, integer 32 format. This leads us to JAXPRs, which stands for JAX expressions. These expressions are JAX's intermediate representation of operation sequences. Think of JAXPRs as a simple way to represent a functional program broken down into its most basic operations. When we look at JAXPR for our CLU function, we can see the precise sequence of primitive operations, including constants and calculations. This intermediate representation is crucial for JAX's internal workings and plays a vital role in the optimization process during just-in-time compilation. Now let's explore pytrees, which are an important concept in JAX. While JAX's functions and transformations primarily work with arrays, developers often need to work with collections of arrays. For example, when working with neural networks, you might organize your parameters in a dictionary where each key points to meaningful arrays. Rather than creating special handling for each type of data structure, JAX uses the pytree abstraction to handle these collections in a unified way. This abstraction allows JAX to work consistently with various data structures that can be treated as pytrees. When we examine the pytree structure by printing out the JAX tree leaves, we can see our actual values populated within the JAX pytree abstraction. JAX provides several useful tools for working with these tree structures, including functions like JAXTreeMap and JAXTreeReduce. Finally, let's discuss how JAX handles pseudo-random numbers, which works quite differently from other programming libraries like NumPy. When generating random numbers in JAX, we need to use a specific approach. First, we must import JAX's random library. Unlike other libraries that maintain internal state for random number generation, JAX uses a stateless approach where we need to explicitly track the state ourselves. To generate random numbers, we start by creating a key that will track our state. When we examine this key structure, we can see how it will help manage our random number generation. For example, if we want to generate a normally distributed random number, we need to provide this key each time. An important detail to understand is that using the same key will always return the same random number. The random number generator doesn't automatically update the key for us. We need to manage this explicitly. To generate different random numbers across multiple operations, we can use the random split function to create new keys from our main key. By using these subkeys, we can generate truly different random numbers at each iteration. This approach gives us more explicit control over our random number generation process, even though it requires more manual management compared to traditional NumPy-style random number generation. If you'd like to support the channel, consider starting a free trial of our new design tool, which is linked in the description, and let us know what you think. We'll include a link to the Getting Started documentation in the description as well. If you have any questions, please post them in the comment section, and we'll do our best to respond. Thank you very much for watching to the end, and please enjoy it responsibly.